So this year we're doing, we've added some new MySQL users to our keynote speakers. So we'll hopefully provide some thought-provoking real-world use cases that you'll hear over the next couple of days. And the first of those is, I'm pleased to present Renjish Abraham. Renjish is the Tech Lead DBA for Dropbox database operations, where he focuses on automation of everything MySQL. Before Dropbox, Renjish was also a tech lead at YouTube, where he led the MySQL operational efforts. And he loves to automate to the point where his scripted minions do all the work for him all the time. Please join me in welcoming him to the podium.
Thank you for the intro. Good morning, ladies and gentlemen. Oops, sorry. Okay. Good morning, ladies and gentlemen. My name is Renjish Abraham. I'm a tech lead at Dropbox. I primarily focus on Dropbox operations and infrastructure. And I'm here to talk about what Dropbox is, what are the issues that we ran into while scaling Dropbox operations, what are the lessons learned, and what is the future work that we have to do. So what is Dropbox? Dropbox is a pretty popular product that is used by several millions of users to sync files and contents across multiple devices and platforms. The file syncing process is essentially done by multiple file entry points. One of the file entry points is the Dropbox client that runs across your laptops, your mobile devices, as well as your desktops. Another file entry point is your web browser. You can upload files using your web browser as well. There are also third-party platforms that use our APIs and sync data over to Dropbox. Once this data is synced over to Dropbox, Dropbox immediately resyncs this data back to all the devices for a particular user. In this way, we maintain multiple copies of the same content within Dropbox as well as across all the devices for a particular user. Now let's take a look at the Dropbox architecture. At a high level, it is pretty simple. We would also like to keep it very simple and straightforward. So at the heart of this process lies the Dropbox clients. These are nothing but agents that run on your laptops, mobile devices, as well as your desktops, and continuously monitor changes that are happening on the magic folder, which is nothing but the Dropbox folder. As and when it detects a change, it starts talking to our web servers, and then the actual file metadata information is then transferred over to MySQL. It is important to note that within MySQL, we just have the file metadata information. We do not have the actual files. So where does the actual files reside? We make use of Amazon S3 infrastructure to store all these files. The clients ensure that the files are chunked, encrypted, and sent over to Amazon. But the most important thing is that as we chunk, we also store this block information within our MySQL metadata, within our MySQL servers, because we want to reconstruct this data back, and that's how a download process works. Now let's take a look at some of the numbers that we see on a daily basis. A small caveat here, these numbers are like 6 months old, and unfortunately I can only share numbers that are publicly announced by us. So we have more than 200 million users. We do more than 1 billion file syncs a day. We have tens of thousands of physical servers present within our data center as well as within Amazon's. We have several thousands of MySQL servers, and we are more than just file syncing. We do camera uploads, and we also provide rich APIs for platform integration. So now let's take a look at our user growth. So we started sometime in 2008, and we had a dedicated set of users. As we gained more popularity and kind of attained the critical mass, that's when we started seeing a spike in our user growth. So every few weeks or every few months, we started rapidly doubling our user base to the point where by November 2012, we had 100 million users. And within a year, we had 200 million users. So the whole point of my talk today is, what is the impact of this hockey stick user growth on our database infrastructure as well as database operations? And before I go to that particular thing in detail, I would like to spend a few minutes on why we chose MySQL, because MySQL is also an important component here. That is where we store all our metadata information. So the most obvious answer is it is free, and it is the most popular open source DBMS. One of the important things to note here is that MySQL being the most popular open source database management system means that there are a whole bunch of users and community members who have run into problems and have identified solutions. So most of the problems that we may potentially run into already have some kind of working solution. The other most important thing with MySQL is its predictable performance characteristics. For example, MySQL is very good when it comes to in-memory index lookup, and it also is pretty good when it comes to small range scans. You can always expect it to perform a particular query of this type within a few milliseconds or within sub-millisecond range. But there are also certain workloads that make MySQL totally unpredictable. But if we can control this workload, then we can ensure that we have consistent performance guarantees. So what are the workloads that we have to avoid? The first one is avoid cache churn as much as possible. An example would be if you have long-running range scans, you're better off sending it to the slaves. Another one would be reducing instances of excessive background activity by MySQL, like say purge lag or insert buffering. So this can also be, majority of the cases where this happens is when you have aggressive writes going on to the masters. And mostly it is the batch jobs, and if you can throttle these batch jobs, then you get into a much better state. And finally, it's the I/O subsystem performance. This is also an important factor here. And this is one of the reasons why we chose to run MySQL instances within our own data center. Because we can control these factors, and we can also profile the hardware that we want. We run all these DB benchmarks and kind of figure out that, okay, this particular set of RAID setup with SSD devices or Fusion.io is going to make things much better. All right, now let's get back to the core of this talk today, the impact of this huge user growth on our database infrastructure as well as database operations. So our backend infrastructure is modeled pretty much after the most common setup. You have a bunch of memcache servers. You also have a bunch of databases. At this point, you can also assume that these database servers consist or comprise of monolithic database servers as well as sharded database servers. Now, when a request is sent by the web server or the front-end server, it first goes to the memcache layer. If the data is not there, then it fails over to the database. And then on its way back, it populates memcache and goes back to the web server. But as we started seeing a huge or significant ramp up in user growth, what happened? Of course, we had to double the number of front-end servers. And as we increase the number of front-end servers, the number of connections to both memcache and database significantly increased. And this is the number of connections per instance. And memcache is really good when it comes to handling several thousands of connections. Memcache can easily handle 50K connections. While MySQL, it was good at 10K. And as we started increasing the number of connections, we went to a point where we were running like 20K connections per instance. And we would run into these weird performance issues every now and then, because whenever you have a burst in traffic, what happens is that even simple things like a show process list would stall the MySQL server. And just as a note, we were running on 5.0 or 5.1 version of MySQL. So the problem here is that whenever there is a burst in traffic, the entire system kind of slows down. And another problem is that we have a lot of cross-database transactions. So when when the web server connects to two databases, opens two transactions, and one of the databases is slow, it naturally has to keep the other transaction open and possibly acquire a row lock. And when this happens, with the other database slowing down, you're just extending the time the row is being held. And if the web server were to time out or a fresh request comes for the same set of rows, now you start getting into the problem of row locks as well. So this is where this cascaded problem starts happening, and the overall system performance starts to degrade. So we had a couple of options. One is to migrate to a better version of MySQL, assuming that it takes care of this problem. But at that point, we were not confident that the latest versions of MySQL would handle this problem well. And also, we wanted to have our own database proxies, because the moment we introduce our own database proxies, we have more control over what is happening. So what was the whole idea behind our own database proxies? So the proxy acts as a connection pool and ensures that the number of dedicated connections to the database instance is pretty low. So from 20K connections, we dropped down to 200 connections during steady state, which is remarkable because all these connections now from the web server just hit the DB proxies, and the DB proxy can easily handle 15K or 20K connections. And we had multiple instances of the proxies also running, because these proxies were written in Python. And of course, there are also some problems that got introduced by proxies, but I don't want to get into the details of that. I just want to talk about the good details. So, but this is how the proxy helped us scale as we started seeing this huge spike in user growth. Next up, flexible schema. So why do we have to think about flexible schema? As we started becoming more and more popular, we also want to introduce more and more features so that you keep the user engagement better. The thing is that most of the features tie to actual schema changes. And it is possible that the schema change can be on a very small database or a very small table that is not sharded, or it could be on a very large table that is sharded. If it is going to be on a very large table that is sharded, you have to kind of look at easily spending 2 to 3 weeks just rolling out the schema change. Unfortunately, we do not use any online schema change tools. The reason being, our metadata is very, very important, and we ran into some data inconsistency issues when we ran the online schema change tools. So we take this time-tested approach of making the changes on the slaves first, and then rolling them as masters. But the thing is that while it is ensuring us that we have consistent data, it is also going to take a lot of time. And that is why we introduce flexible schema. So what is flexible schema? In the standard setup, 10 different attributes are stored in 10 different columns per row. Whereas with flexible schema, what happens is that you store these 10 different values as key value pairs within a blob. And once you provide APIs to the front-end engineer on how to scan this data, how to look for this data, and how to update this data, the problems are solved. And we can also index this data depending on certain types of attributes that the front-end engineer wants. So the biggest benefit here is that an attribute change, which earlier translated to a column change, now just becomes addition of more attributes to the blob. And the natural progression of flexible schema was database as a service layer. This just extends the notion of APIs and abstracts it even further. So what is the abstraction that we get? The front-end servers now just issue application-level RPC calls. They just do something like commit batch. What it internally does is totally not within the domain of the front-end servers. The DB as a service layer now knows exactly how it should translate these to the actual SQL calls, route to the appropriate databases, handle cross-database transactions, and then return the results back. One important benefit of DBA as a service is that we could add throttling mechanism to DBA as a service. So an example would be if you have a thundering herd situation where you restart all your web servers, or there's a sudden spike in traffic. Once you have a throttling mechanism in place within DBA as a service, it is okay if we serve 99% of the traffic and start short-circuiting 1% of the traffic because we cannot handle it. We are still in a better state because it is okay for us to comply within our latency limits and not overall degrade the system, if not for this throttling mechanism. So the biggest thing that we learned out of this is that database as a service is the way to go as you increase the number of database instances within your cluster. Next up, what was the impact on database operations because of this huge ramp up in user growth? I mean, we continuously were doing promotions and deployments for system upgrades, MySQL upgrades, this continuous loop of sharding, database splits, merges, as well as cloning and all draining operations. So a good side effect of this is job security. And we are just 2 database administrators within our team that maintain like 3,000 servers or more. So we were continuously bombarded by these requests. So what was the immediate side effect of this? We started writing a lot of tools, automating them, and making this process better. But after a point when you step back and look at what has happened, you just see close to 30 or 40 different scripts that only few people know how to run because these scripts are pretty invasive. They can bring down the site because if the promotion goes bad or if one of these slave failovers go bad. So that is now a new set of problems. You introduce automation, and by automation now you have another set of problems. And that is where we took a step back and said, a common framework and a unified interface is how you got to deal with database operations at scale. So by using common framework for database automation, you have code reuse, well-tested code reuse. And the other thing with unified interfaces, anybody within our infrastructure team can do some of these activities because you kind of abstract away all these internal calls and everything. It's just a click of button. So we have this interface called DB Manager that we use to perform almost all these activities that I mentioned. We can do massive number of promotions in parallel. We can do massive number of cloning in parallel. We can do sharding, database splits, and there are also a few more things that we want to integrate within this DB Manager unified interface. But this is one of the important lessons that we learned. All right, so far I've been talking about the impact of user growth and how we modified our approach, our processes, our systems to help us scale to this demand. But these are components that we had complete control over. There is one entity in this equation where we did not have full control over, and that is MySQL. So we can tune the hell out of MySQL, but still there are some areas for improvement within MySQL. I think I'm running short on time, so what I'm going to do is I'm going to quickly go over some of the areas for improvement. And the reason why I bring it up here is we don't have a MySQL engineering team, and the expectation is that MySQL, as well as the MySQL community members, look at some of these areas for improvement and kind of prioritize them. Because it is pretty important for users of MySQL to also have a better product. So the first one is single-threaded performance, replication speed up, and the baseline for these are the 5.5 version that we use. I do agree that some of the improvements are already live, but still there is more area for growth here. Online schema changes. I mean, it's great that 5.6 has online DDL changes, but the thing is that it is more directed towards applying this on the slaves and not on the masters. Stored procedures. I mean, it'll be such a big improvement if we start using stored procedures as the means of communication between our front-end servers and our actual database as a service layer, because you just make one call rather than making these entire transaction one statement at a time. Faster recovery, and as well as data fragmentation. I'm not sure if this problem has been addressed even in the latest versions of MySQL. So what are some of our areas for improvement? That is our future roadmap, our areas for improvement. So the first one is migrate our entire backend infrastructure to database as a service, because we know it works. The next thing is to eliminate or reduce the dependence on monolithic databases, because these are single point of failures and don't scale well. We want to enhance our DB operations to a controller agent model. That is, we have this unified interface, but also having a controller agent model and a native protocol to just do administrative tasks is going to be really, really helpful. And finally, we also want to focus on compression, because our data footprint, the disk size, is continuously increasing. So we are not running into performance issues as such. The problem is that we continuously run out of disk space, because we have so much metadata that we store. It's like more than 1 petabyte across several thousands of instances, and this is continuously happening. So we want to introduce compression and kind of deal with all the performance-related issues because of compression. So what are the lessons learned at scale? The first one is database as a service definitely works. A common framework, unified interface for database operations definitely works at scale. And MySQL has some areas for improvement. I would finally like to conclude my talk with this slide. We are hiring. We are on the lookout for awesome talent to join us and contribute to the overall success of our team. Please feel free to either contact me or talk to any of my colleagues at the booth in the exhibition hall. We also have a networking event. I think it is tomorrow evening, and we look forward to seeing you all there. Thank you.